Okay, hi there. Today we're going to be continuing section 2.2 in the calculus chapter. And we talked about the constant rule and the power rule, but what about some derivatives of trig functions? So one derivative or two derivatives that we're going to look at are the derivative of sine of x and the derivative of cosine of x. The derivative of sine of x is cosine of x, and the derivative of cosine of x is the opposite of the sine of x. Some of the things we looked at as far as the graph goes, notice that this is our graph of sine of x in the top graph here. And notice that from negative pi over 2 to pi over 2, that the graph is increasing. And notice that from negative pi over 2 to pi over 2, the graph of cosine of x, which is the derivative, is positive. So when the original function is increasing, notice the derivative is positive. Similarly, we can see that as the original function sine of x is decreasing, that our derivative is negative. So just take a look at some of those relationships. I think that's pretty cool. Well, anyway, let's just use this to find the derivative. So the first one is just y equals 2 times the sine of x. We're not going to be writing the dx in front of everything. That's pretty much what we're doing. But we just want to take the derivative of each of those sides. And so if we were to do that, that means that we would have dy dx. And then we can pull out the scalar multiplier 2. And then we would want to take the derivative of sine of x. And we just learned that the derivative of sine of x is cosine of x. And then we would simplify. So that means that our dy dx, you could actually happy cloud that, but I'm just going to get rid of the parentheses, is equal to 2 times the cosine of x. Let's look at letter B. In letter B, we have f of x equals 1 over 2 times the cosecant of x. And notice we haven't learned anything about cosecant, but we do know something about sine, and cosecant is the reciprocal of sine. So let's make sure that we bring this up first. And it ends up looking a lot nicer. So this is really the same as 1/2 times the sine of x, right? Just bring the sine of x up. And so then what we can do is, again, just take the derivative. So I'll just call this f prime of x. And then we have 1/2 times whatever this derivative is. Again, the derivative of sine of x is cosine of x. And so basically the derivative f prime of x is going to be 1/2 cosine of x. Or you could write cosine of x all over 2. Okay. In letter C, we have y equals x plus the cosine of x. Notice that we have a sum, so we're going to use the sum difference rule here. And that means that we are able to take the derivative of x and then the derivative of cosine of x and then add those together. So let's take the derivative of y, so that's going to be dy dx or y prime. We know that the derivative of x is just 1 times x to the 0, or just 1. I'm sure you're fine with that by now, plus, and now we want the derivative of cosine of x. Well, we just learned that the derivative of cosine of x is the opposite of sine x. And then we'll just clean it up a little bit. 1 times x to the 0, like we said, is just 1. And instead of plus a negative sine x, we'll say 1, and then we'll just say minus sine of x. Okay, so you'll have a couple questions where we'll just utilize the derivatives of the sine and cosine functions as defined by theorem 2.6. So now that we've talked about that, let's get into some things that are a little bit more exciting. And one of the things we're going to be looking at are rates of changes. So derivatives can also be used to determine the rate of change of one variable to another. So some applications would be population growth rates, production rates, water flow rates, velocity, and acceleration. And again, a common rate problem deals with the motion of an object in a straight line. And back in Algebra 1, we learned how to compute the average rate of change of a function, y equals f of x, over a specific interval. We didn't use the subscripts 0 and 1. What we did is we usually used x sub 1 and x sub 1 and x sub 2. But here we're just looking at it between x sub 0 and x sub 1. We know that to find our rate of change, we can take delta y, which is the change in y, which means basically your f of x sub 1 minus f of x sub 0, or like y1 minus y0, and delta x is our change in x, here x sub 1 minus x sub 0. So this is what we can do to find our average rate of change. Delta y over delta x, or change in y over change in x. And essentially this is just our slope formula. And we use this when we want the average rate of change. But again, just think about this as the slope formula. F of x sub 1 is just a value of y. F of x sub 0 is the other value of y. So just make sure we're careful of the order and go from there. Okay. And it turns out that the average rate of change over that is going to be the slope of that secant line, right? That's going to be that slope. So let's find the average velocity of a falling object. This says if a ball is dropped from 100 feet, its height s at a time t is given by this position function. And the position function in this case is s of t equals negative 16t squared plus 100. Now s is going to be in feet, t is in seconds. And it wants us to find the average velocity over the following time intervals. So anytime they're asking for the average velocity, this is where you're essentially going to use that slope formula. Okay. So what that means is that we're going to need to find the, I'm looking for my gray pen, I can't find it. Here's one. We're going to have to find the values. We have the x values, but we're going to need the y values, which in this case are going to be my s of 1 and my s of 2. So I need to find the output values. So for s of 1, I'm just going to put 1 into this equation they give us. And I have negative 16 times 1 squared plus 100. So that's going to be negative 16 plus 100, which is 84. And then I can do the same thing, negative 16 times 2 squared plus 100. And so that's going to be 4 times negative 16 is negative 64, plus 100 is 36. So those are going to be those values. And so the average velocity, I'll just mark it as a sub v, is again going to be our change in y over the change in x. Our change in y is going to be s sub 2 minus s sub 1. And then our change in x is going to be 2 minus 1. So my s sub 2 was 36. My s sub 1 was 84. And then again, our x values were 2 and 1. So that's, I guess I could just write that as 1. Okay. And 36 minus 84 gives me negative 48 over 1, so negative 48. Okay. So what that tells me is that my a sub v is negative 48, and we should put a unit on there. Now, my change in y, or I guess my change in s at this point, represents the in feet, and my change in x, or the t, is in seconds. And so the unit that we would have on this velocity, average velocity, is negative 48 feet per second. Now you might say, well, why is it negative? Remember that velocity is speed and direction. And so that's just telling you that the object is going downward, essentially, because that's negative. So between 1 and 2 seconds, the object is going downward, which makes sense because it drops, so it's always going downward, but I digress. All right, letter B. Now let's find the average velocity between 1 and 1.1. So again, that's between 1 and 1.1 seconds. What's the average velocity? So we're going to need to find S of 1, which we found over in letter A, which was 84. But now we're going to need S of 1.1. So we're going to take negative 16 times 1.1 squared plus 100. And you can punch that in your calculator. I know y'all are capable of that. And I ended up getting 80.64. So now that I have the y values, I can now find the average velocity. So again, I'm going to think about change in y over change in x, or in this case, technically change in s over change in t, okay? And I'm going to take s of 1.1 minus s of 1, and then subtract the two inputs, the t values of 1.1 and 1. So this gives me 80.64 minus 84 over 0.1. And that gives me negative 3.36 over 0.1, and that can just simplify to negative 33.6. So between those two times, the average velocity is negative 33.6 feet per second. Okay, so notice that the velocities were different depending on what times we were dealing with there. What if we wanted to know what the velocity was at a specific point? How in the heck could we do that? Well, I have great news for you. Now that we have an understanding of limits and derivatives, we can define the instantaneous rate of change of y with respect to x at x equals x sub 0. So this is going to be the instantaneous rate of change, and that's going to be our velocity. So I didn't want to label these as the velocity because it was the average velocity over like a specific interval of time, but our derivative can help us find our instantaneous rate of change. So notice that to find the velocity, we're going to take the limit of our change in y over change in x as our change in x goes to 0. And so essentially we have the difference quotient. So what this is telling us is that our velocity is the first derivative of the position function. Okay. So again, our velocity, v of t, is the first derivative of the position function. And again, velocity does have magnitude and it also has direction. Just FYI, and we'll talk about this a little bit more in section 2.3, but when we talk about our position function, that's often defined as S of t, and that's usually in feet. And then we often refer to the velocity. So our velocity is going to be S prime of t, and that is going to be measured in feet per second. And then if we wanted to find the rate of change of the velocity, that's going to be the acceleration. And what we're going to do is take the derivative of the first derivative. That's called the second derivative. Again, we'll talk more about that later. And the unit there is feet per second squared. Okay. So this is just a little FYI that I have for you. We'll talk more about it later. But just so you know, this isn't going away. Well, usually the S of t is our position function. We take the derivative, S prime of t, that represents our velocity. And then eventually we'll be taking the derivative of the derivative. to find our acceleration. Also, just the difference between velocity and speed. Speed is the absolute value of velocity. So if I wanted the average speed in this question, it would be 48 feet per second. But the velocity tells us that it's going downward at that speed, okay? So example 14 wants us to find the instantaneous velocity of a falling object. It says if a ball is dropped from 100 feet, its height s at time t is given by this position function, s of t equals negative 16 t squared plus 100, where s is in feet, t is in seconds. Familiar, right? Because it's the exact same wording as example 13. The difference is that this time they're asking for the instantaneous velocity at 3 specific times. So if we want the instantaneous velocity, what that means is that we're going to need our s prime of t. So let's find that s prime of t, okay? That will be what we do first. And so if I want s prime of t, so I don't know, I guess I'll write s of t. So here's s of t, negative 16t squared plus 100. Okay. Let's find s prime of t. We're going to take the negative 16 as the coefficient, and then we take the derivative of t squared, which is going to be 2 times t to the first. And then by the constant rule, the derivative of 100, which is a constant, is 0. So essentially, my derivative ends up being negative 32t. Okay? And remember that this s prime of t is really the same as the velocity. And remember that our units would be in feet per second. Sometimes we forget that later. We'd like to put that in our answers. Okay, so now that we have that, let's find the instantaneous velocity at the intervals. And so that would be what we do second. Second, what we're going to do is just substitute at those different intervals. So let me do it at 1 second. I can find s prime of 1 is going to be negative 32 times 1. So s prime of 1 would be negative 32, and then I just put my unit on, feet per second. Can you tell that's a prime? Okay. All right. Now let's find it at 1.1. So s prime of 1.1 would be negative 32 times 1.1. And negative 32 times 1.1 is negative 35.2. So I'll just, again, label it with that unit, feet per second. And then at 2 seconds, we can find s prime of 2. That's just going to be negative 32 times 2. So s prime of 2 is negative 64 feet per second. And that is the instantaneous velocity at that point in time, okay? So that's kind of a lot nicer than the average rate of change, which is over a period of time. We can say that when the object, like at 2 seconds after the object is dropped, this is the velocity. And that's something that we couldn't have done before without our calculus. It's very exciting. And if you guys look at the relationship between these instantaneous velocities and then the average rate of change, you'll see that they match up. But again, it's just so much nicer for us to be able to compute that instantaneous velocity using the derivative. And again, just note that the velocities are negative because the object was moving downward, the object was dropped. So that means that all the velocities would be negative. Okay. So the last thing we're going to look at today is this idea of the position of a free falling object with no air resistance. This can be given by s of t equals 1/2 times g times t squared plus v sub 0 times t plus s sub 0. This probably is familiar to you either from Algebra 1 or Algebra 2, or I hope both. But this is basically the position function, okay? And this should say can be given by, sorry, okay? So again, this is our position. Now in the past, we always had like negative 16t squared. The reason is because g represents our acceleration due to gravity. And when we talk about things measured in feet, the acceleration we would talk about being feet per second squared. And our on Earth, the acceleration due to gravity is negative 32 feet per second squared. So 1/2 times negative 32 is what gives us that negative 16. So if you're like, well, it was always negative 16 back in Algebra 1 and Algebra 2, and that's because of that gravity constant, okay, that we have on Earth. Again, S sub 0, you might remember, is the initial height, your starting height. V sub 0 is your initial velocity, so the velocity it starts at. Again, g is this acceleration due to gravity. We have that it's negative 32 feet per second, or negative 9.8, sorry, negative 32 feet per second squared, or negative 9.8 meters per second squared. I would, just to be on the safe side, have these options memorized. Okay, just make sure that those are two things that you know, that it's negative 32 feet per second squared, or if your position is being measured in meters, you can use negative 9.8 meters per second squared. Okay, and of course t is our time. So let's use our derivative to find the velocity. This says that at time t equals 0, a diver jumps from a 32-foot high diving board with an initial velocity of 16 feet per second. When does the diver hit the water? Well, let's see what we have here. This is a 32-foot high diving board. That must be where the diver starts. So that's going to be my S sub 0. This tells me that my S sub 0 is going to be 32 feet. The initial velocity is 16 feet per second. That tells me V sub 0. Now, will this be a positive 16 or a negative 16? Well, let's think about the diver. Like when you dive, you don't just, you kind of like, you jump up a little bit, right? And we kind of see that that's happening here. So our velocity is going to be positive if we're jumping from a diving board. And then when does the diver hit the water? If the diver hits the water, that is looking at the end height. And so that's going to tell us what the position is. Oops, sorry. That the position, S of t, is going to be 0. And so our goal here would be to find t, because it's asking when does the diver hit the water. Okay. So our starting position is 32, our initial velocity is 16, and then again the position that we're looking for is 0. So we can put all of those pieces into the puzzle. We've got 0 equals negative 1/2 times, sorry, 1/2 times negative 32, because again, our gravity constant is going to be negative 32 feet per second squared, because we're dealing with feet per second and feet here, okay? So 1/2 times negative 32 times t squared, plus my v sub 0 is 16t, and then, or is 16, and then times t, and then plus my s sub 0 is 32. So essentially, I've got negative 16t squared, familiar, right? And then plus 16t plus 32. So let's solve this equation for t, and that will tell us when the diver hits the water. I can factor out a negative 16, and that leaves me t squared minus t minus 2. And then I can continue factoring. This is nice and factorable. I love that. And we find that the solutions are that t is 2 or t is -1? Well, it's asking when the diver hits the water, and we can't have a negative time since we can't. So we can just see that our answer will be that t equals 2. So we can see that the diver hits the water after 2 seconds. Okay, so that's an algebra problem, right? Algebra 1, maybe review an algebra 2 type of a problem. Letter B, however, says what is the diver's velocity at impact? Again, when it says at impact, that is going to be an instantaneous velocity. So if we want the instantaneous velocity, we're going to have to find v of t. And again, the instantaneous velocity is the derivative of our position function. So that's what we're going to have to do first, we're going to find the derivative. And our position function was that s of t equals, and so again, up here, our s of t was 0, but this is really then our s of t function, -16t squared plus 16t plus 32. So let's find our derivative, s prime of t, because that's going to be our velocity. So this is going to be, I wish I could talk to you guys. Are you guys good with saying -16 times 2t to the first and just jumping right to -32t? I know you can't talk back to me right now. Okay, and then here we have just plus 16, and then that ends up being 1t to the 0, which is just 1, and then the constant ends up being 32. So here's my derivative. My derivative is that s prime of t equals -32t plus 16. Okay, now that being said, it wants the velocity at impact. So that is at a specific amount of time, but what do we mean by at impact? Well, what is the diver impacting? It's when the diver's hitting the water, right? So the impact is when the diver hits the water. So when did the diver hit the water? Oh, we did that in letter A, after 2 seconds. So we're going to evaluate at t equals 2 seconds. So our s prime of 2 would be -32 times 2 plus 16. So we can see that's going to be -64 plus 16, which is going to be -48. So it would be -48 feet per second at impact. Okay, and that is a little bit about how we can use these derivatives to help with things like instantaneous rate of change. Okay, so that's it for today. You guys have a great one, and we'll see you next time in 2-3.